So this year I'll have a very interesting update on all the new chemistries that are coming up and the chemistries that you can already use now. So I will look first at the capacity and impedance trends to see where we are right now, so that you could choose the best chemistry for your particular device. And specifically, I'll look at the trends of the impedance change, because it is not actually just the capacity that matters, but the battery impedance as well. And then we'll look at what is available now in terms of different battery chemistries. And specifically, what can you do in terms of the cost reduction and making the materials more available. Of course, the other big area is the high charge rate capability. For some applications, like industrial applications, you also need to have very high longevity. So there are some chemistries that are best for that. And finally, we'll look at what will come in the next 5 years. So what are the most interesting chemistries that are coming up pretty soon, and futuristic technologies. So first of all, let's look at where we are right now. So this is the plot you might have seen before. It shows energy density versus year. And you can see that the capacity energy, the energy of the batteries keeps increasing. Although your traditional 18650 cells has been overtaken since then by the pouch cells, because that is where most of development is going. But the important part is that energy density keeps increasing. But one other thing is to keep in mind is that you also have to consider the power capability of the cell. And to do that, you actually need to look at the impedance of the cell. So how can we compare impedance of the cell? One thing to keep in mind is that the cell impedance is inversely proportional to cell capacity, so you cannot just compare it directly. So first you need to normalize impedance to the same capacity, for example, 1000 milliampere hour. And after that, you can compare cells one to another. And so this plot here has been generated by using our entire chemical ID database that is more than 4,000 different chemistries are summarized in this small diagram. What you can see from here is the most important part is that the typical 1000 milliampere hour impedance is around 300 milliohm. So if your normalized impedance is higher than that, that means this cell is optimized for high energy, and or it is bad. So you have to consider it. You need to know in what particular segment you are buying this battery. So you can see that the typical cell phone battery is actually around 400 milliohm normalized impedance. And the ones that are optimized for tablets are close to somewhere like 500, 600. But if you are higher than 600, that has to be either highly specialized high energy cell, or there is some problem with this cell. So you really have to consider, check it out for your application. On the other hand, for high power applications, you want to be below 100 milliohm. So typical powered cells are around 100 milliohm region. And if you are below that, then your cell is actually great. Then it is even better than originally intended. And some cells that are literally designed almost as to be a supercapacitors, they can be even below 50 milliohm. So what can we do from the point of optimizing our design based on the cell impedance? So important thing is to understand is that there is going to be a compromise between energy density and impedance. So you cannot just pick a cell with a very low impedance, because in this case that means you will have low energy density. So you can see overall picture of energy density versus impedance, and you will see that there's definitely a trend of cells with a higher energy density having basically higher impedance, which is generally bad for power capability. So you cannot just choose a cell that's going to be optimal unless you want to pay a huge amount of money, because another axis that is not shown in this plot is cost. So if you pick a very expensive cell that uses some exotic materials like nanotubes or something like that, you can get actually low impedance even for high energy density cell. But in most cases, you will have to follow the general trend. So why is it bad to have a higher impedance? Well, obviously, if you discharge at the extremely low rate, your open circuit voltage will look like this black curve. So basically, you will have almost no loss of runtime. But if you discharge at any substantial rate, it will look like the blue line here. And this would be for a low impedance cell. For example, for your application, in this example, it is somewhere around 1C rate discharge. Now, if you would go to the higher impedance cell for the same rate of discharge, you will follow the purple curve. And the purple curve will reach termination voltage, which is the voltage where your system is going to shut down. It's at 3 volt, much earlier. So you will have some capacity loss, which we call here delta Q. So it's basically loss of usable capacity because of the cell impedance is higher. And so generally, this is just the physics, and so you cannot do anything about it, except that you can try to design your system to get the most out of this behavior and not leave any capacity on the table. So how can that be achieved? This can be done if you have a gauge that measures the voltage across the cell, a temperature across the cell, as well as has a powerful MCU that can model all the needed processes, flash memory that allows you to update the battery parameters, and also the smart algorithms that allows you to continuously update the parameters of the battery, such as the capacity, impedance, and finally provide you the prediction of remaining capacity that allows you to shut down only when you need to, and definitely not earlier than that. So how that could help you? Well, first of all, the important part is that you need to be able to update this impedance not only for the steady state loads, but also for variable loads. So with impedance track gauging, you can typically update only with the loads that are somewhat steady. But we recently developed a dynamic Z-track system, which allows us to update also under any variable loads. So for all of our new gauges, it will be available both as impedance track as well as the dynamic Z-track choices. And so important part is if this R, which is in this case the low frequency impedance, is being updated across the entire age of the battery, you can predict the runtime to the point where your system actually shuts down and not to some kind of arbitrary high voltage point. In order to make this dynamic Z-track work, we do a wide bandwidth characterization of the cells. So in this example, you can see a discharge relaxation profile that is typically used for our battery characterization, which will give you open circuit voltage of this battery, as well as the impedance, low frequency impedance, that is you can see on the right bottom side, and the impedance spectra at all different states of charge. So you can see that impedance spectra at different state of charge actually change. So the impedance spectra is highly dependent on state of charge, but you can also see that the high frequency, which is on the left side of this impedance spectra, actually changes little. And that is why we can use this for things like temperature correlation, for example, or even to use it for some things that change little with state of health. But with the aging, also the low frequency of this impedance will change, and that is why we need to keep updating it constantly in system. So here is what you can get a benefit by using impedance track gauging. So if you are using the OCV-based termination, which some of the competition devices are actually using, or some simple MCUs are using, you will actually terminate at the point where this delta Q basically will occur. Well, in this example, it's quite large. You will lose close to something like 17% of your runtime if you terminate at 3 volt. But in this example, your system actually can go to 2 volt. The minimum the shutdown voltage of the system is actually 2 volt in this case because you design your system well, or this is a multi-cell pack, for example. So your electronics is actually capable to go to 2 volt. So you have absolutely no reason to terminate at 3 volt, but the only reason why you're doing that because you don't have a battery modeling and you are assuming that you have to do it. But if you use impedance track gauge, you can actually set the terminate voltage to your actual system capabilities, like in this example, close to 2 volt, and you will get the entire runtime that is not significantly reduced even though your battery impedance is higher because you chose a high energy capable cell, for example. So in this example, you will change your delta Q from something like 17% to something just a couple of percent. Now, this delta Q will increase with the battery age, but impedance track will keep updating impedance information, and so it will still stay accurate. So you can still rely on shutting down based on our full battery modeling instead of shutting down just based on some arbitrary voltage threshold. So this is one example how we can get additional runtime by using accurate gauging. Now, the other area where impedance increase is affecting us is actually charging rate. So you might hear from some publications or media that somebody came up with a charging algorithm that can charge any cell in 5 minutes or 10 minutes, and it will be great. But in reality, the charge rate of the battery is determined also by its impedance. For one side, if you apply very high current to the cell, it will just instantly go to CV mode, and at this point, your current will start dropping. And there is some absolute fastest possible charge rate for any particular battery impedance, basically. I call it a critical current for this cell, and that critical current will decrease as battery impedance increases. So you have seen for the trends, based on the trends, the high energy cells will actually have a lower critical current, and so you will not be able to charge them arbitrarily fast. But another problem with the cells is that most of the cells using graphite anode will have lithium plating if you charge it on an extremely fast rate, also because of the battery impedance. But in this case, it is the anode impedance that is the most important. So if you look at the picture, you can see the potential on your anode. In this case, it is graphite anode. And what is the potential? This is something you can measure if you insert a reference electrode and measure the voltage difference between reference electrode, in this case lithium, and the anode. And in the beginning, when it is not fully charged, you will be very far from lithium. So your potential will be far away, so you will not have any lithium plating danger. But as you charge more and more, you're coming closer and closer to the lithium. And so eventually, you will actually never cross below 0 if you are charging at low rate. But if you're charging at fast rate, you will actually have IR drop across your anode, and that IR drop pushes potential lower. And at some point, you can actually reach potential where you will have lithium plating. Now, in the normal cells, you will switch from your CC charging to CV charging earlier than before you reach actually this threshold. But when battery ages, the anode impedance will keep increasing, and eventually it will reach a point you will start having this lithium plating even if you use the specified charging rate. And that is basically the point where you have an exponential drop-off of capacity. So here's how it looks typically for fast charging cell. So if you charge the cell at a low rate, in this particular case, 0.5 C, you will get the red line. So it will be a very nice linear degradation of capacity until you reach about 80% of original capacity. So this is all good, linear, and predictable. And so at this point, you didn't reach lithium plating because you're using a slow charging rate. But it is not acceptable to use a slow charging rate for most applications. So mostly you want to use a specified charge rate, which is in this case 1 C rate. So in this case, if you use specified charge rate, you will actually, at some point, the impedance of anode will increase, and you will actually have lithium plating. And that is what happens when you see this quick drop-off and the exponential drop-off of capacity. By the way, that is the same point where bad things happen to the cell. For example, gas evolution will happen, and so that will also cause a cell swelling. So this would be actually the point where you would want to take out this cell from the system. And so for this reason, we actually developed cell swelling detection algorithms that allows you to detect this moment and also replace your cell. But ideally, we should prevent this from happening. And for that reason, we developed a max-life charging algorithm, which will model the potential on the anode and tell the system the current that it needs to apply to prevent this lithium plating from happening. And that is what would be this green curve here. So you can see this green line. It shows basically the same degradation across the whole life of the battery, but close to the lithium plating threshold, it actually stays linear. So even though we're doing a fast charging, but we are actually avoiding these lithium plating regions, and so we stay linear across the whole life of the battery. So if you continue this cycling, which we did actually, it stays linear even until the 70% capacity loads, for example. So it extends the usable life of battery significantly. Now that I talked about the overall picture of the different battery trends, let's look at the specific chemistries that are available right now on the market, and also after that I'll go to the more advanced new chemistries. So here is a picture, kind of a snapshot of all the chemistries that are out there right now. Important part is that maximum voltage has increased. When I made this picture for the first time, actually the maximum voltage was 4.2 volts. By the way, it is some kind of a misprint here. It should be actually 4,600 millivolt. So before it was 4,200 millivolt for the fully charged cell. But now it is 4,600. That means we have increased by close to 300 millivolt in the last 15 years that I have been doing this presentation. But what's interesting is that also that the density, which cells are the most typical right now, as shown by this red and yellow colors. Those are the most typical cells. And the blue color means that the voltage is never there, or maybe light green means the batteries are rarely there at that voltage. So you can see that the most common cells are right now actually already close to 4.5 maximum charging voltage. Now, on the other hand, the other big trend here that you can see is that not all of the cells have this sharp drop-off that the graphite has been originally having and lithium cobalt oxide, but you will see a more smooth drop-off at high DOD range. So this smooth drop-off happens due to two different trends. On one side, nickel is becoming more common, so NMC, different type of NMCs have a more sloping voltage profile. And so you have a little bit less energy density for this reason, but on the other hand, capacity is larger. So actually, overall energy remains the same. But you need to make sure that your system can terminate at lower voltage, otherwise you will not get this additional capacity. The same thing is additional silicon being used on anode is also starting to make this drop-off less sharp than graphite. So I'll have more details on that as well. But this is, you can already see that in overall trends, because a lot of the cell density voltage is now in these shallow regions and not all in this sharp drop-off region. So let's now look specifically at each of these most popular chemistries. So the most popular chemistry for the portable application still remains lithium cobalt oxide. Even though cobalt is a problematic metal in terms of supplies, but it still gives you the highest voltage, highest energy density, especially if you charge it to 4.5 volt, which is actually become common these days. Now, if you want to get a little bit more availability of your cathode material, you can go to some variety of NMC. And there are many different NMCs. So NMC stands for nickel, manganese, cobalt. And you can have, for example, NMC 532 means you will have 50% of nickel, 20% of manganese, and 20% of cobalt, for example. But right now, there is a lot of trend towards going to higher nickel content. To use this chemistry, I mean, you can achieve the same energy density as with lithium cobalt oxide, but cheaper, basically, and more available. So, but you see that it has a more sloping voltage profile. And so you need to make sure that your system can run to lower voltage, otherwise you will lose some of these additional capacities. Like in this example, if you terminate at 3.4 volt, you will lose close to 10% of capacity, basically. So it is really a lot of waste of usable energy. So you need to design your system to be capable to go to, ideally to 2.7 volt at least, if you're going to use NMC chemistries. Or you use a multi-cell, many cells in series in order to get this overall voltage per cell to lower level. That is why this chemistry is already popular in multi-cell systems like notebooks and power tools, but not so much popular in single-cell applications, because there they cannot operate usually to anywhere lower than 3 volt per cell. So the other side of the spectrum is movement towards even more cheap and even more available materials, because even nickel become actually a little bit less available, given that about 20% of it is manufactured in Russia, and so it being under sanctions affected the supply of nickel. So many people already started looking under iron, for example. as a replacement. And lithium iron phosphate is the ultimate cheap cathode material because it uses extremely available iron, and phosphorus, which is also available, is basically fertilizer. So everybody can make lithium iron phosphate. But its disadvantage, it has a lower energy density, because if you look at the voltage, it is instead of 4.2 volt you are seeing here, maximum charge voltage is about 3.6, 3.7 volt, and the flat main plateau is around 3.4 volts. So it's a much lower voltage, but it has other good properties. For example, it has an excellent cycle life, so typically it can reach 2,000 cycles instead of 1,000 cycles. It has a good power capability if it is designed right. So you can, this is the demonstration that was shown by using up to 40 ampere in actually power tool cell, and it was still holding off the voltage. That means impedance of this cell is extremely low. No, but of course people are trying to have a both of, they're actually trying to get both great things, both low cost as well as higher energy. So there is a lot of development to try to increase the voltage of LFP. And how can you do that? And you can do that by replacing some iron with another cheap metal, which is manganese. And that is the way how LMFP was born. So LMFP has a voltage profile with two steps. One step is higher, that is the higher voltage due to the around 4 volt due to manganese. And the second step is the usual traditional LFP kind of a behavior. So, of course, from gauging standpoint, that's actually a little bit better than LFP, because at least you have one region where voltage is changing. LFP is actually extremely difficult from gauging standpoint, and we had to develop some special gauging algorithm to support these flat portions so that we put a low weight for this flat portion of the voltage regions. But so with the MLFP, this problem will still remain, but at least it gets a little better, because now you have two steps. Problem is with MFP is not fully stabilized yet. There's a lot of still research going on to make them stable, because right now this higher plateau disappears first with the aging, and the lower plateau stays. And so that means that your OCV will actually change during the cycling, which is not ideal for gauging. So here a few words about actually the difficulty of gauging of this. So if you compare just the traditional lithium cobalt oxide voltage profile with LFP voltage profile, you can see the difference right there, right? So you can see that the same amount of voltage change, you will have just less than 1% of SOC change for LFP, and you can have up to 15% SOC change for this chemistry. And so how do we address that? Is that we developed algorithms that actually computes the weight for each of the measurement depending on the flatness, and we will correspondingly handle the previous estimate of SOC and new estimate of SOC according to this kind of a weighing algorithm. And that is how we can support LFP without drastically improving voltage measurement accuracy, although we did improve voltage measurement accuracy as well. So we are approaching this from two directions at the same time. So finally, for the grid application, sometimes it's not enough to have 2,000 cycle life. There is another anode material that replaces graphite, which is called lithium titanate. That allows actually battery to achieve 20,000 cycles. Now, this is really a dramatic improvement in cycle life. Now, unfortunately, this material also has a lower energy density. So if you look at it, this is even lower than LFP. So the voltage of it is only, maximum voltage is 2.7 volt. And the kind of flat portion voltage is around, 2.4 volts. So it's even lower than LFP. But for some applications where you need a very high longevity, this still can be an excellent choice. It also has very good low temperature capability. So if you need to, let's say, make sure that your car will start at low temperature, or some other application that needs to operate at low temperature, this is actually a good chemistry as well. So this is pretty much all the chemistries that we have available now. But let's look at something that's coming now, already being tested right now in this moment. So just a brief overview what we can generally look for in different chemistry directions. Generally, it has intercalation materials or conversion materials. So all of the materials that I have been talking so far are intercalation materials. So graphite, for example, is intercalation anode, and lithium cobalt oxide is intercalation cathode. What it means is that we are putting lithium ion in in that material without breaking the crystalline structure. So it just expands, but it doesn't break. The structure stays constant. For conversion materials, when you insert lithium, it actually breaks the structure and forms a new chemical material. And that is why, so far, there has been no real stable battery that developed with these materials. Conversion materials could be fluorides, chlorides, and chalcogenides, but one big problem, like one big advantage of them is they give you a much higher energy density. So with conversion materials, you could increase energy density by about 10x. But that is why there's still a lot of research going on. If you look at the research papers right now, many of them will be actually in conversion materials because everybody is having this far away goal to achieve the much higher energy density. So this would happen at some point, but so far we are staying with just the intercalation materials. And most promising right now is actually silicon for the anode and CMA 89 for the cathode, which is some particular variety of NMC. So I'll look at each one of them a little bit closer right now. So first of all, silicon. That is a replacement for graphite that you can see from this picture has close to 10 times higher capacity compared to graphite. You can just clearly see it from this capacity plot, potential versus capacity. No, you can also see from this plot that silicon potential is slightly higher, which means that it will add capacity more in the lower voltage region of the curve. And that is one reason that you need to actually make sure that your system is capable to go to lower voltages to take advantage of this material. But another problem with it, it expands a lot. So this 10%, this high capacity for lithium intercalation means it turns from the solid material that you know, the silicon is basically a solid metal, to some mesh that looks like plastic, basically. It's extremely soft and very much expanded. And so if you do that inside your battery, it will crack. So there are a lot of stable passivating layers that are formed in graphite, for example, don't work anymore with silicon. So people had to completely redesign the battery electrolytes, battery additives, the battery materials themselves to add them more solidity to them and give some space for the expansion of silicon before the cycling of silicon was enabled. And so people have been working on silicon for the last 20 years at least, but no, there is lots of application cells are already available, and actually we characterize many of them already for our chemical AD database as well that uses silicon. So what approaches different startups are taking to solve this expansion problem? One approach is to grow nanowires. And there are several startups that are already in the kind of a sample production with the kind of nanowires. They moved from growing this extreme picture like here that to really grow perfect nanowires on top of some solid material. It turned out to be not practical. It was just too expensive. And it requires sealant gas, which is also flammable and not very easily available. But they came up with several different tricks that also allows to grow wires, but with a little bit cheaper methods, but less perfect. And so the cyclability is still not as great as they were originally showing with this kind of more expensive materials. So the other approach people are taking is the micromatrix. So that approach is, it uses solid matrix, which is, for example, graphite matrix or some hard carbon matrix. And into it is embedded just the chunks of solid silicon. So you don't have to grow it using very expensive material like sealant. So it is much cheaper, in principle, to manufacture this kind of materials. So this method has also demonstrated quite good cyclability. So several startups demonstrated cyclability up to 1,000 cycles with the same energy density increase that you expect from silicon, about 30% increase of energy density. But it turns out that it also has additional benefits. For example, because this carbon matrix has very good conductivity, and silicon actually is a fast material for fast alloying reaction, it also shows a very fast charging capability. So anyway, it actually demonstrated the 5-minute charging. Basically, they were using 10C rate charging, basically. So it is possible with silicon to go to extremely high charging rates. So one other benefit of silicon, if it is designed right, is that it has a good performance at low temperature. So you know that with traditional graphite anode, the diffusion rate of lithium into solid graphite becomes extremely low at low temperature. And so that is why this lithium plating that I was talking about starts at basically right at the 0C. So both for charging and discharging as well, you have a very big kinetic limitations at low temperature. But for silicon, that problem is not as prevalent because, again, it is an alloying reaction. And if you have a good conductive matrix, you can actually have a pretty good discharge rate at low temperature. So they demonstrated close to 50% capacity at -20, for example, which is completely impossible for graphite. So that means that your car, for example, with this battery could be used at low temperature. You could at least start from wherever it was parked and drive somewhere before it actually heats up during the operation. So this is quite important for a cold start of a battery. Important thing is also for cold charging of a battery as well. So on the cathode side, a lot of interesting developments are also going on. So one important development on the high side, or like basically the highest energy density side, is this NCMA that I mentioned earlier. So NCA 89 was basically replacing, going to very high concentration of nickel. So going to basically 89% of nickel to make it on one side cheaper because you almost have no cobalt. But on the other side, with that much nickel, the batteries usually were unstable. So the safety was problematic and cycle life was not so great. But when people combined that kind of two materials, one is using manganese, and another one is using a high amount of nickel, but combining the two together allowed to make this NCMA 89 actually that has the highest energy density of any batteries out there right now. And that is actually being manufactured by LG, and GM and some other automakers are already starting to use this cell. So this is the highest energy density you can get right now for automotive batteries. Now, the other direction is to make batteries not higher energy density, but cheaper. Because this problem with these nickel-based batteries is that nickel is still quite expensive. And quite a rare metal, actually. If you look at just the abundance of nickel compared to, for example, iron, it's still going to be 3 orders of magnitude lower, right? So what do you want to replace it with to be completely cheap and abundant is manganese, because manganese has almost the same abundance as iron, and it's quite widely available, used very heavily in metallurgy. So for that reason, there is a lot of development to try to push the content of manganese while still keeping high energy density. And that direction actually resulted in the lithium manganese-rich chemistry, which is this LMR. So this has been announced recently by GM and Ford that they're doing developments in this direction. And so the idea of this material is quite interesting. So it contains manganese in higher oxidation state. Normally, manganese in higher oxidation state is not stable for cycling. It was more of a conversion material, actually, because it falls apart. But in this particular design, when it is combined with some small amount of nickel and some other dopants, it actually stabilizes the structure. And that results in a relatively high voltage, actually 4.5 volt as well, and potentially they can go even higher voltage, and decently stable cycle. So there's a lot of developments going on. This is actually one of the most researched area right now because it promises the same cost as LFP effectively, but with energy density of NMC. So you can think about that as a cheap version of an NMC with the same energy density. Right now, there are some problems that has to be solved with it. One problem is that voltage actually unstable and changes with the cycling. And you can see here in this picture. So by itself, it's not terrible, but you do lose some energy density when doing that. And so your energy density basically decreases with cycling faster than it otherwise would be. Second, it causes problem for gauging as well, because now in our gauge, we have to account for the change of voltage with the cycling. The same thing, by the way, happened with silicon as well. So we are actively developing algorithms that will continuously model and change the voltage with aging. And we will be able to support in the future also such chemistries as LMR. At this point, we don't have samples of them yet, so if anybody has any sample of it, please send it to us. So one other active area of development is going on is actually extending the life even further. So typically, the spec for the portable application cell cycle life is about 1,000 cycles. But for automotive, that is already almost not quite acceptable. So for automotive, they require 2,000 cycles at least. But if you want to have a car that could go for 1,000,000 miles, for example, how many cycles do you need? Actually, not that many. You need about 5,000 cycles under very drastic conditions, or 10,000 cycles under more mild conditions. It would push you to a million-mile car. That actually has been demonstrated, interestingly, with these single crystal NMC materials. And so single crystal NMC is not that difficult to make. It's basically the same NMC, it just has to be baked slightly differently, and with the focus on crystalline shape. And with this kind of materials has demonstrated these amazing cycle lives. And this is NMC, it's not LFP or all these exotic materials that I was talking about earlier, like titanate. So titanate has a long cycle life, but it also has low capacity, low energy. But this material actually has high energy, like any normal NMC, but also very long cycle life. So I have high hopes that this single crystal NMC or other developments will keep the cycle life increasing about 5,000, 10,000 cycles. And that will be extremely useful for automotive as well as the grid storage. But why is it actually important for automotive? I mean, if you think about it, do you really need a car that will go for 1,000,000 miles? Because you might want to change the car before that. Well, one reason for that is you could use your car, electric vehicle, as your cash bank, because you can buy electricity at the cheap prices. For example, in Texas, electricity is very cheap during the day or in the night when a strong wind is flowing. But there is a gap between the day and night where electricity becomes extremely expensive. It actually increases in price by about 20x. So you can buy the cheap electricity during the day and sell it during this gap period, maybe between 7 p.m. and 8 p.m. You can make good amount of money. People calculated that individual car user could earn about $400 a year doing that if your grid would support it. But you would have to cycle your battery a lot more to do that. And your system would also have to support bidirectional charging. So TI is actually developing bidirectional charging support devices. So you can look up bidirectional charging, and with TI there's quite a few application notes available of how to do that. And this is definitely a lot of effort is going on the electronic side to support this, as well as on the battery side to make battery cyclable. Because if your battery is the old-fashioned one, you might want to not cycle it because you will be afraid that you will lose your runtime. But with this kind of batteries, you don't have to worry, right? So some other direction that is also very actively explored right now is for the grid storage specifically, how to handle the situation where we will not have enough lithium. I mean, you have seen in the first presentation, the trends of the battery capacity increase are just stunning, right? We are doubling the battery capacity almost every couple of years. And so where is all this lithium is going to come from? Many people are wondering. So at this point, there is no shortage of lithium yet, because there is a lot of new mining projects, the new production, new refining that actually is going online. But in the future, it is true that lithium is quite a rare metal. And so its abundance compared to iron, for example, is again 3 orders of magnitude lower. So one solution for that is sodium. It turns out that a sodium battery actually has almost the same energy density as lithium battery. If you think about it, how is it possible? Because sodium is much heavier than lithium, right? But if you look at what has weight in a battery, it's actually cathode materials, it's the graphite, anode materials. All of these things, weight of them is much bigger than the weight of actual ion or actual metal that is being used for energy storage. And so when people actually make calculations, it turns out that the sodium battery has only 20% less energy density compared to lithium battery in a lot of applications. And then when people design sodium batteries using different approaches that are available, for example, using oxide cathodes, Those oxide cathodes are basically metal oxides, like iron, manganese, nickel, the same materials that you use right now in NMCs, basically. So the cathode was not that difficult to create. After some experimentation, they made some materials that have a little bit higher volume so that sodium can go inside them. And on the anode side, people replaced graphite, which is actually too dense for sodium to go in, with hard carbon, which has a much bigger volume and easier path for the sodium. And by combining these two, the energy density turned out to be quite decent, just 20 to 30% less than traditional NMC, and actually close to LFP, what's interesting. So at this point, sodium battery, as is, already starting to compete with LFP in terms of energy density and at cost. Even very early samples already, they're still quite expensive. You can actually buy sodium batteries now. They're a little bit more expensive than LFP at this point. So by itself, it doesn't make sense yet. But there is a trend. If you look at predictions of how the cost of sodium batteries are going to develop in the future, it's going to basically drop like a rock in the next 10 years. And so at some point, while LFP right now costs about $70 per kilowatt hour, the sodium battery will cost $40 per kilowatt hour. So this price, electric car will actually become cheaper than traditional, the internal combustion car. And it can be used basically everywhere for battery storage, energy storage, and so on. So that is definitely a very hopeful direction. We already released some chemical IDs for sodium cells, and I'm very impressed, actually, that have excellent low temperature capabilities as well. It turned out to be unexpected benefit of it. But so many people actually tried to use sodium battery already for applications that need a low temperature performance. And so that kind of justifies the little premium compared to with LFP right now. But in the future, they're going to be completely cheap because right now in LFP, about 30% to close to 50% of price is coming from lithium. But sodium price potentially is zero, right? Because you can get it for free from the oceans, from your kitchen soil, from your soda. It's everywhere. So it's very abundant metal. So speaking about the future, so if we want to theoretically to achieve the highest possible energy density of the battery, I mean, how long do we have to develop new batteries? What's the end point? So we need to look at the periodic table of elements to see theoretically what is the best possible highest energy dense material. So on one side, we have to go up because up are the light materials. So on the top of, the very top would be hydrogen, but hydrogen is a little bit difficult to deal with because it's gas. So we settled on lithium. So lithium is already giving you the highest energy density as a metal because it is light and it is on the left side, which means it has the highest ability to give away electron. Now on the cathode side, we need to also pick something from the right. Not ideal gases, but something like fluorine would be the best because fluorine is the most reactive gas and it is the lightest gas as well. It wants to take away electron, but unfortunately it is so reactive that you cannot keep it in anything. There is literally no bottle that you can keep fluorine in. It reacts with everything. You can actually keep it in aluminum because it passivates, but there are some couple of tricks you can use, but generally it's a very toxic gas, so you don't want to deal with it. So luckily, the oxygen is widely available for us because the nice live creatures already generated it for us using photosynthesis. So oxygen we can just grab from the air. So if you would grab oxygen from the air and lithium, that will give us the highest energy density battery that is basically theoretically possible. And I'll show in a few seconds actually a whole plot of different energy densities. But what is the next best thing? Let's say oxygen is difficult because you have to catch it from the air. So sulfur actually is another next promising candidate because it is right under the oxygen and still quite light. And it is also very abundant. So this sulfur is available as a waste product of the energy in the oil and gas production industry in huge amounts. So on the other hand, sodium, I already mentioned, is right there below lithium. So sodium is also quite a good material, maybe not for the highest energy density, but for being much more abundant than lithium. So let's look at what energy density we will get with those materials. So right now we are somewhere on the right side of this picture. If you look at the carbon C6 lithium cobalt oxide, you can see it is quite small. It is about 500 watt-hour per kilogram. So you have a lot of ways to go to reach the left upper portion. That's where we want to be. So in the left upper portion is lithium oxygen, as I mentioned. So that one can have close to 5,000 watt-hour per kilogram. So it is 10x increase compared to where we are now. So you can see there is a lot of ways to go to get there. But so people are already working to try to achieve that, but there's a lot of problems with it. There are some intermediate values like zinc oxygen is actually also quite high energy density, is close to 2,000, and that is already used in hearing aids as a kind of a primary battery. But it's difficult to make a cycle. And then, of course, lithium sulfur, lithium peroxide are also up there, around 3,000. That is some other direction people are working on. So let's look at what people actually try to implement. So lithium sulfur is one of the most actively researched. So lithium sulfur theoretical capacity is 2,500 watt-hour per kilogram, but practical cells are about 10x lower. So why is that? First of all, you need to add a lot of conductive additive because sulfur is a great insulator. So you need to pass the electron to sulfur and from sulfur to make a battery. And sulfur does not want to pass electrons. So one solution to that is to add a lot of conductive additives that is nano level, such as nanotubes or some kind of graphene. But all of those things are quite expensive, and they also occupy volume and space. And that is why you lose energy density effectively. The other solutions is to use some kind of a soluble sulfur and make a water-soluble solution of sulfur, but that is also expensive. On the other hand, lithium itself is problematic because lithium, you cannot use lithium metal directly with, say, water solvent or any other solvent because it reacts with everything. So you need to create some kind of solid electrolyte barrier if you want to use metallic lithium with sulfur, for example. So that is causing a lot of issues as well. So, but nevertheless, a lot of developments are going on. And so for applications like aviation, for example, energy density is the most important part. And so there are some experimental systems that are already flying around the Earth. I think the highest record for the longest flight by electric aircraft has been already demonstrated using lithium sulfur batteries, for example. But those are prototypes that are extremely expensive and they're nowhere close to mass production. So, of course, the ultimate goal here would be the lithium air, because I mentioned that is the highest energy density, 5,000 watt-hour per kilogram. And people already demonstrated this battery. I mean, it is not even new. That it actually has been done first in 1996. It does do what you would expect. It has a very flat discharge because metallic lithium has a flat, basically same potential everywhere. And then it drops off when your lithium is finished. The problem is if you look at the charging curve, which is on the right side here, you see the charging voltage is much higher than discharge voltage. And that is because you have to expel the oxygen. Basically, you have to have a phase transition between solid and gas. And oxygen is a gas. So you lose a lot of entropic energy loss by this transition. So there are some theoretical limitations in energy density of charging, energy efficiency of charge and discharge for this lithium air battery. So that's one of the reasons why it is not yet widely used. Another big reason is that this cathode material that you have to make have to capture oxygen from the air. Now, oxygen doesn't want to react so easily. So you need to add a lot of expensive additives like catalysts, platinum, iridium, things like that. Pack basically your cathode with these materials, which makes it extremely expensive. That is one reason why also we don't have in mass production any fuel cells as well that operate, even though the fuel cells also have a similar principle. They have to capture oxygen from the air, but they use a very expensive catalysts to do that. But some of these problems could be solved if you use, instead of oxygen, if you would use peroxides. And so one good thing about peroxides is that they are solids, so you will not have a phase transition, so you will not have this entropic energy loss right away. Also, you don't need such expensive catalysts to have the reaction going. And so with lithium peroxide battery has been demonstrated It has a pretty decent theoretic capacity of 1,300 watt-hour per kilogram. And they show decent cyclability as well. So that is one promising direction that some companies are already working on. One problem is safety, because peroxides are not that stable. And you know, if you heat them up, the oxygen will be released. And if you have some kind of a short circuit going or something going on, it will start burning. So from that point of view, these applications could be used more of in the grid storage in some places where they're far away from populated areas, something like that, and not necessarily in portable applications or cars. So some other directions that lithium is being used is actually trying to use metallic lithium with the traditional cathode materials. So that is what the so-called solid electrolyte battery or just solid battery is. I mean, media has a lot of frenzy going on about the solid battery, but what they're talking effectively is using metallic lithium with the solid electrolyte that will enable its protection, and traditional cathode materials, basically the same lithium cobalt oxide, the same NMCs that everybody were using before. And the problem with the metallic lithium in general is that it forms dendrites, and that is why, even though it has a higher energy density, of course, than the graphite or silicon, you also have a huge expansion as well, because you basically start with 0 and then you deposit some metallic lithium. And if there is any crack or defect in this solid electrolyte, it can go through. Also, during the deposition of metallic lithium, there is such a thing as critical current. So if you exceed this critical current, it breaks through that, again, the solid electrolyte, and you will have a short, or in the best case, your battery will be damaged, but in the worst case, you might have a safety event, because metallic lithium is extremely reactive. So that is why people keep working on different solid electrolytes, improvement of solid electrolytes. So it's a very big research area. But right now, there are some samples that already appeared with the solid electrolyte battery. We actually got, for the first time, a lithium metal battery actually sent to us for chemical ID characterization. But it requires a pressure. So you need to apply an actual pressure on the cell when you operate. So that, of course, will also decrease somewhat the energy density, because now you need to account for the energy and the volume of your pressure rack, basically, that keeps it pressurized. So that is one of the other problems that needs to be solved. So manufacturability of solid electrolytes, cyclability of metallic lithium, getting rid of these high pressure requirements. That is a couple of main problems that still remains before the solid, lithium metal battery will be used widely. So that is pretty much everything I have. So again, to reiterate, some of the main trends are that 8650s are barely growing anymore in capacity, but pouch cells are still continuing growing. So a lot of still research and improvements in energy density continues. And impedance, normalized impedance peak is around between 200 and 400 milliohms. So you can check your battery normalized impedance and see where it will be compared to the typical battery. But it also means that you need to use a smart impedance track gauge that actually accounts for impedance and allows you to get the max out of your battery and not just rely on some kind of voltage-based termination that loses a lot of capacity. So right now, the silicon is the most popular new material that's basically becoming available, but it requires some new algorithm developments to account for this OCV change. And NMCs continue developing and reached now very, very high energy density with this almost 89% of nickel in it. And of course, the sulfur, lithium sulfur are continue being developed, but still not widely available. The single crystal NMC, I expect, will become more and more widely available to achieve the highest possible energy density, but also, the cycle life, but also it needs to be supported with additional electronics, such as the support of bidirectional charging. We are supporting all of these different chemistries. We're releasing chemical IDs with accounting for these new effects, such as OCV changes. And so we'll continue supporting all of them for you to be able to use it in your applications and adapt it and achieve the best results that you are trying to achieve in each of your devices.